Then let's look back at what we learned about functions. Because we looked at many different functions, and we defined and used the concept of derivative for all of them. And now my question is going to be about what the derivative is of a function. And I would like to look at calculus 1 that studied functions from a line. Function f was from a line to a line. And you introduce notation like x, y, and composed a plane out of those lines, and studied function geometrically using graph, studied function in different ways, and you studied derivative. And then in the beginning of this class, we looked at functions from a line to a plane or to free space. So that was a different kind of function. And then we never looked at the graph, but we understood and used the concept of derivative. And now we are looking at functions from a plane to a line. And now we introduce notation for the derivative, and we just talked about what it is. So what is the derivative? So the expression concept is a vector of at every single point there is a vector. Now, where is that vector? Is it in R2 or in R or in R3? It's in R2. It is in the domain. So this is where the gradient vector is. Let's suppose if I'm there. Remember that? Vector made by derivatives. Only algebra. But where is that vector? Is it in the domain? Is it there? What was the meaning of that f prime? What was the meaning of f? What was the meaning of r? That was time. Usually thought of that line as time and function describing the motion of a particle and the position describing the position of a particle. So f of t is a point on a plane, and what was the prime function? Awesome. That was velocity vector. Vector again. Sort of the same concept showing up. So it's a vector, and that vector is there in the target space, not in the domain. Should we go back? Calculus 1. What is this? Well, that's a number. Right? Well, it's okay. We didn't study vectors in calculus 1, so it's a number. But where is that number? Is it here? No. Is it there? No. It's on the graph. It's somewhere out there, and not exactly the point on the graph, right? But something we usually imagine the rate of change, the slope of that tangent line. So that number is nowhere, essentially. You cannot draw it, either here or there, or even on the graph. Just say that while you draw the line and imagine that slope. And we call all these things the derivatives. Isn't that strange? In three different situations, we have totally different setups. We call the same word the cause of that leads sometimes in the domain, sometimes in the range, sometimes nowhere. And we persistently call derivative. What is it that we have in common? Because there must be something. You better find something in common.
Linear behavior at some point evaluated in your wherever your function is.
So it is an object, yes, it is an object, the derivative is an object describing linear behavior of a function, describing this linearization. And what I believe is that derivative is the linearization. So the thing is that, or probably the simplest way to see the analogy is through the algebra, through the Taylor series. So you look at the Taylor series for the function of one variable, and you see that the derivative at the point x0 is simply the coefficient with the first term, first degree term. And for that case, now you think of a function being multidimensional. Right? So this is going to be a point in a plane in 3 space. So f of x is equal to f of x0, position at the time x0, plus f prime of x0 times x minus x0. And again, that is a vector being coefficient with the first degree term. And of course, this is just a compactified notation. There were coordinates of f of x coordinate and y coordinate. Just probably write f of t, f of t0, so that you have x coordinate and y coordinate going together. And what we did here, making the vector, is we brought those derivatives of x with respect to t and y with respect to t together, making a vector. So, but those derivatives are coefficients with the first degree terms. And in this case, we have the same thing. We have f of x should be f of x y, right? Let's keep treating x, y as coordinates in the plane. We have f of x0 point 0 plus the partial with respect to x, so x minus x0, plus the partial with respect to y times y minus y0. And a lot of other terms. But we looked at these two terms, we put these two numbers together, and we said, okay, well, it's convenient to look at these two numbers together as a vector. Well, see, algebraically, there is no vector here, just two numbers. Right? And algebraically, and sort of simplistically, you can think of derivative being the set of all coefficients. Just all the coefficients you have with the first degree terms. All the coefficients you have with third degree terms And that will continue forever. If you have a function from high-dimensional Euclidean space to another high-dimensional Euclidean space, it will have the Taylor series, it will have coefficients with the linear terms. Just put them, all of them together, and that's the derivative. Now, the specific implementation of how to think about a bunch of numbers is a different story. Right? It may be convenient to put these numbers together and to think of them as vector here, or as a vector there, or as a vector elsewhere, or as a matrix. Because if you go from a plane to a plane, you'll have 4 coefficients, and you'll see later they make a matrix, and that matrix doesn't belong to any of the 2 planes. So you'll run into a situation like that, when derivative is again nowhere, and that's okay. Algebraically, it's okay. You just have a bunch of numbers to deal with. And those numbers measure something, no problem.